Okay, we're ready to come back to chirality. So here's where we left over in our last lecture, which is assigning the absolute RS stereo configuration. Right, so this is a process we will be taking, which is locate the chiral center, identify the 4 substitutions you have, and then assign priority from highest to lowest. And remember, for priority, you're looking at the atomic number directly connecting to that chiral center. And guys, are you ready for the class? All right. So coming back, this is what we went over, right? So first, assigning the priority of the substitution based on their atomic number. If they have the same atomic number, you look at one more atom. So for example, we're looking at this chiral center. That's the only chiral center we have in the 2-fluorobutane, right? So in this case, if we're thinking about it, on this carbon, the fluorine is having the highest priority group. And then you have 2 carbons and 1 hydrogen. The hydrogen is for sure the lowest priority group. And then for the 2 carbon, we'll go one more step to see which one is higher. So for this carbon, the next one attached to it is a carbon. For this one, we only have 3 hydrogens attached to it. So this one has higher priority than this one. Or the acyl group has higher priority than the methyl group, right? So 1, 2, 3, 4. So that's how you identify the priority group. And we'll orient the molecule, so the group of lowest priority is directed away from you. So I'm just going to use one of the molecules here. So we orient the group so that the methyl group, the lowest priority group, the hydrogen is pointing away from you. The fluorine comes wedged out. This one acyl, the second one on the right, the third one here. And then you read the 3 group, 1, 2, 3, and we're doing clockwise. So this one is a R stereo configuration. All right. So just a quick reminder in what we did in our last lecture. So getting started on today. So you'll get lots of practice in assigning chiral center in later this week. And today we'll be introducing one more term, which is Fisher projection. Well, 2 more terms. One is Fisher projection, which is something that's very commonly used in biochemistry. You'll see that coming back you're coming back in biochemistry, 153. And then we'll talk about the concept of meso compounds, which are molecules that have chiral center, but the entire molecule could be achiral because it has internal mirror plane. And then we'll do a quick summary of everything we discussed, and then the application of chirality in experimental setup. So that's an overview for today's lecture. So getting started, first of all, Fisher projection. So Fisher projection, like what we did, Newman projection, Fisher projection, these are different ways of drawing the molecule. So if we start from the normal wedge dash configuration, let's look at this one again. Again, what we have, right? So you have the chlorine, and then you have the methyl. Assuming my chlorine and methyl, these 3 defines a plane, which is my chlorine, the green one, the methyl, these 3 group defines a plane. Then my acyl group is wedged out, my hydrogen is dashed in on the back. So looking at it, we went over this one being 1, 2, 3, and this is a R configuration. All right. And in Fisher projection, what we're doing is changing the perspective. So we're looking through the chemical bond from top to bottom. Or the other way to put it is we're looking at the molecule from a different perspective so that both my chlorine and hydrogen are wedged out. The acyl group and the methyl group are both dashed in. The wedged out group are in my horizontal plane. The dashed group are on my vertical. So this is drawing the normal wedge and dash configuration into a different projection, or looking at the molecule from a different perspective. these two are same molecule looking at the different perspective. And then when we draw the Fisher projection on the paper, we draw it like this. On the top, you have CH2, CH3. On the bottom, you have CH3. And then in here, on the left, you have hydrogen. On the right, you have chlorine. All right. So when assigning stereo center for Fisher projection, this one is a little bit tricky. So thinking about it, when drawing my hydrogen on the horizontal, or my lowest priority group, what we're saying is this lowest priority group is wedged out in this perspective. So if my lowest priority group is on the horizontal, we have to switch that RNS configuration. Or in this case, if we look at it, it's like 1, 2, 3. We're actually coming up to be counterclockwise. But because my hydrogen, or the lowest priority group, is on the horizontal, we have to flip. Or the priority group number 4 on this side, or horizontal, we have to flip that RNS. Okay. And the logic is the same as our normal assignment. Is if you put the lowest priority on the front instead of on the back, you're effectively flipping the RNS. So let's look at it again with its enantiomer. Yes?
So if the H is on the vertical axis?
We're getting there.
Oh.
So now let's look at its enantiomer, which is this one. Now, again, we're putting it in a way. Okay, so first of all, let me just demonstrate like these are enantiomers to each other. All right, so you can clearly see these two molecules are enantiomers to each other. You have a mirror plane that's converting the left one with the right one. So now let's focus on this one here. So putting it on our normal perspective, which is the wedge dash perspective. Again, setting my chlorine, carbon, methyl group as my plane, which is chlorine, carbon, methyl group as my plane. My ethyl group is wedged out, my hydrogen is dashed in. All right. So we can assign my RS stereo configuration to be 1, 2, 3. It's going this way, and this one is S. That's what we expect, right? They're enantiomers, so we're flipping the chiral center. And changing the perspective, in this case, this is what we look like when we look at it from a different perspective. So now you're putting the chlorine and the hydrogen on vertical as dashed in, and on the horizontal, these are wedged out. Or on Fisher projection, we draw it out as Cl, and on the bottom, that's hydrogen. On the left, we have my ethyl group, and on the right, we have my methyl group. Right, and similarly, 1, 2, 3. And now, since my hydrogen, or number 4, priority is on vertical, we can use our normal idea of clockwise being R, counterclockwise being S. So this one is my S. Let's do it again, like rotate. Maybe we can do it this way. Let's put it in the same configuration of putting my carbon in the middle. And on the top, I have my CH2, CH3. On the left, I have my chlorine. On the right, I have my hydrogen. and I have my methyl group. So these two are the same. We're just changing the perspective of looking at the same molecule, right? And then assigning the stereo configuration. 1, 2, 3, going this way. But my hydrogen is on the horizontal, so this one is still S. Yes?
So to draw the Fisher projection, will you be given like that first one?
Well, so to draw the Fisher projection, we can give you like this molecule and ask you to draw the Fisher projection. Like for this one, which is the S stereoisomer, both this conformation and this conformation, these are identical. These are both correct. So for Fisher projection, the most important take-home message is that rotation of your Fisher projection by 90 degrees will switch its absolute stereo configuration. So for Fisher projections, you cannot simply rotating the Fisher projection. It is a specific drawing. Yes?
I know you might have already explained this, but what's the reason why you switch the configuration from RS or S to R based on the hydrogen placement?
So this goes back to our original assignment. So in the original assignment of the RS absolute stereo configuration, note that we always put the lowest priority group directing away from you, right? But in the Fisher projection, if that lowest priority group is on the horizontal, then that means this one is wedged out, it's pointing towards you. So that's why putting the lowest priority group on the vertical is okay, but putting it on the horizontal, you have to flip it. Okay, yes?
So are we saying that you can't determine the stereochemistry based on the Fisher projection?
Yes. So based on the Fisher projection, let's do an example together. Let's do a more complicated one. So this is why biochemists love Fisher projection, because in biochemistry, we're constantly looking at molecules like sugar molecules that has lots of chiral centers. Like in order to quickly assign the RS configuration of these chiral centers, the Fisher projection is very helpful. So let's just do these examples together and see how do we do it. So on the left-hand side, this is a D-glucose. We're not covering the DL configuration. You'll learn that in biochemistry. But now let's just focusing on assigning the stereo configuration, like assigning RS for every chiral center. First of all, looking at the D-glucose, how many chiral centers do we have? We have 1, 2, 3, 4. All 4 of them have different groups attached to them. We do not have an internal mirror plane, so it is all 4 of them are chiral center. So how do we do it? Well, let's look at the top one. First, assigning the priority. My oxygen is the highest. And then looking at it, you have 2 carbons. This carbon is attached to 2 oxygen. This carbon attached to 1 oxygen and 1 carbon. So the top one has higher priority than the bottom one. So far, so good. And then you draw it out. Okay, so this goes counterclockwise. But my hydrogen is on the horizontal. So this one is R. Yes?
So why is the top carbon?
Higher priority? Okay, so bear with me one more time. So the question is why this one is higher priority than the bottom one. Look at this. So this carbon is attached to 1 hydrogen, 2 oxygen. This one is 1 carbon, 2 carbon, because you have, 1 carbon. 1 carbon, 1 oxygen, 1 hydrogen. So oxygen has a higher priority than carbon, so the top one has higher priority than the bottom one. Okay.
So double bonds times 2?
Yeah, double bond count as 2. Didn't get? Need to be very careful in not erasing something I need. Okay. And let's look at the next one. I'm just going to use a different color. Now my oxygen will have higher priority. Now if we go up, again, this carbon and this carbon, these two are exactly the same. Both of them has one carbon, one oxygen, one hydrogen attached. But if we go one more, then you got the two oxygen again. This one is one oxygen, one carbon. So the top one will have higher priority than the bottom one. So it's clockwise, but my hydrogen is on the horizontal. So this must be S. All right. And then the third one. I'm just going to do the third and fourth one and without saying anything. And let's check our answer and see if we are consistent with each other. One. Two. So I got R and R. Do we have the same answer? Yes. What's that?
For the second one, I think that the top carbon is higher priority than the bottom.
Well, again, you count it one by one, right? So counting the priority is something like you want to go slowly. So let's do this. So this carbon, how many of them is attached? We have one carbon, one oxygen, one hydrogen. So that's the top one. And you look at this one. Again, this one is one carbon, one oxygen, one hydrogen. So we can't distinguish. We have to go one more further. So looking at the top one, we have one hydrogen, two oxygen. And you go this one, and you get, well, one carbon, one oxygen, one hydrogen. And comparing this with this, the oxygen has higher priority than carbon, so the top one is higher priority.
Yeah.
With me so far? All right, so it is a little bit tedious, but just go slowly along the molecule and counting what are the connectivity on each of the carbons. Yes?
So you just keep going up higher and higher, like.
Right, until you reach something that is different.
Okay, so you just keep going down this chain. What is
Yeah.
it to?
Yes.
What if nothing's ever different?
Well, then is it chiral? If nothing is different, then you have two groups that are identical to each other. It's no longer chiral. And let's move on to the D-fructose and do this again. So again, like practice makes perfection. So for D-fructose, it's the same idea, right? We draw it like this. We start from the first one. We have one. Well, this carbon has two to oxygen, so that's 2, 3. So it's going clockwise, but hydrogen on the horizontal, this is S. Second one, we have 1, and then carbon, these two are the same. This one is higher, 1, 2, 3, counterclockwise. Hydrogen on the horizontal, you got R. And the last one, we have 1, well, carbon, and this one is CH2, top one is higher, and again, R. All right, so Fischer projection is something that's very useful. I don't introduce it just to make your life miserable. It's like helpful to quickly assign the RS stereo configuration when you have a complicated molecule like a sugar molecule. Yes?
So you can't do this for chiral molecules?
You can also do this for like simple chiral molecules. It's not typically worth it. Like drawing the molecule into the Fischer projection will take some energy itself. All right, so this part is a Fisher projection. Again, the Fisher projection is just a different perspective of looking at a molecule with multiple chiral centers. The most important take-home message assigning the RS configuration in the Fisher projection is make sure you read what is the lowest priority group, whether it's on horizontal or on vertical. If it is on horizontal, you need to flip the RNS. So that's a point that people typically make mistakes. Yes.
I'm so sorry. Can you re-explain why CH2O2 is less priority than?
Okay, so for priority, again, when we're assigning priority, what we're doing, I'm just gonna use like a green color and the yellow color. So if we're looking at this chiral center, going up, we have one carbon center. So looking at this carbon is connecting to one oxygen, one carbon, and one hydrogen, right? And going down, we have a carbon center connecting to one oxygen, one carbon, one hydrogen. So we can't tell the difference. We need to go one more step into here. So looking at this carbon, how many is attached? It's attached to one carbon, two oxygen, double bond count as 2. And going down to this carbon, this one is attached to one oxygen, 2 hydrogen. So clearly the top one has higher priority than the bottom one. So before you get familiar, it doesn't hurt to just write out what are the connectivity of each of the carbon centers you have. All right, that's a Fisher projection. And now let's move on to one last topic in chirality before we talk about the summary, which is meso compound. So this is, again, where lots of people make mistakes when we're talking about meso compounds. Now, meso compound is a class of compound that contain multiple stereocenters, but it can also be a mirror image of itself because it contains an internal plane of symmetry. So this is a little bit counterintuitive. You're talking about a molecule can have chiral center, but at the same time, the molecule itself is not chiral. So we'll do one example together, see what that means. I'll go very slowly, but if you have your molecular kit, please view this molecule as we were drawing it. Now we start from what we call like a B3 butanol. So the red one represents a oxygen or a OH group. So let's see, where do I start? All right, so let's start from some kind of conformation. I'm just gonna put it like this. All right, so this is what we start from. I'm putting my carbon, 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 my 4 carbon on the same plane. And how do I draw it on the board? I have something like this. You first draw the skeleton. And then we can see my oxygen is pointing towards me. So that's my oxygen, OH, and OH. All right. We can quickly assign the RS stereo configuration. Now, for both chiral center, my hydrogen is in the back. So we can say 1, 2, 3. This one is R. 1, 2, 3. This one is also R. So it's a RR23 butanol. So that's where we start from. And thinking about drawing all the stereoisomer of my 2,3 butanol. Well, we can first draw the enantiomer of this molecule. Okay, so what does that look like? I already have one built up for you. So thinking about, I want to draw the enantiomer of this molecule. Am I putting it the right way? Let's see. Okay. See, if we have a mirror plane in between, these are enantiomers to each other. And that looks like, oh, this one, this one, this one, and my oxygen comes out. Let's see, 1, 2, 3. That's my S. 1, 2, 3. Also my S. So far so good. We have a pair of enantiomers. And also you can look at this molecule from different perspectives. Like what if we look at the center molecule? We can look at it from the different perspective. This is staggered. We can rotate it. This is eclipse and staggered, eclipse. These are just like different conformation of the same molecule. All right, so these are my enantial pair. What if I want a diastereomer of my 1,3 RR butanol? Let's see. I want a diastereomer. So, well, if I want diastereomer, I just change one of the group into a different stereo configuration. So instead of RR, I want it to be RS. Well, so I'm just moving. Let me see. I want to put it in the same conformation, and I want to just change one of it. Let's see. Okay, so these two are no longer mirror image to each other, and these we can assign the stereo configuration. 1, 2, 3. The oxygen wedged out, and the other one dashed in. We have our S configuration. And note that these two are also diastereomers. So far, so good. And well, at the same time, if I keep my diastereomer, you can imagine, well, we have another diastereomer if we put it SR, right? So if I make it so that the first one is wedged, the first one is dashed in. Let's see, how can we do it? I want the first one to be, let me still do it sideways. So I want this one here. That's it. Right, so it looks like these two are enantiomers to each other. Or I can draw it as coming out. This one is wedged, and this one is dashed. This one being my S configuration, this one being my R configuration. So far, so good. Looks right? But now we're looking at these two molecules, and there's something different making these two molecules actually identical to each other. Now, if I, instead of having the trans configuration, meaning my methyl group are on different sides, I'm just rotating it into the cis configuration. And these two molecules are identical to each other. They're the same molecule. Okay, I'm gonna put it back and then do it again. So this is where we start from. This is where we start from. They look like mirror image to each other, right? But if now I change a different perspective of putting it in here and in here, these are actually same molecule with each other. And these two are called meso compounds. All right, and going back to our definition of the methyl compound, I'm going to read it again with you. So a methyl compound is a compound that contains multiple stereo centers, but is superimposable with its mirror image. So a methyl compound will have an internal mirror plane. So in here, where is my internal mirror plane? It's not very straightforward when we're looking at it in its original, trans configuration, or when we draw it like this. But when we put it into the cis configuration, or when I put it as like carbon, CH3, hydrogen wedged, oxygen dashed. It's now very obvious there exists an internal mirror plane of symmetry. We can also do it from the Newman projection, right? So if we look at the center bond, so assuming we're looking through this center bond, and these two, the methyl group and methyl group are right eclipsing each other. Oxygen, right eclipsing each other. Hydrogen, right eclipsing each other. It's a higher energy conformation, yes, but it doesn't change the nature of the molecule. Like the lowest energy conformer of my molecule will look like this. That's all staggered. But in the Newman projection, you can do free rotation of the single bond, and as long as we have a conformation that you can find an internal mirror plane, this becomes a methyl compound. This is another point that people tend to make mistake. It's after you assign the chiral center, think about it. Does there exist a different way of drawing the molecule, or does there exist a different conformation of the molecule so that we can identify an internal mirror plane? Or some of the questions we might ask you is, can you draw the internal mirror plane of symmetry for these methyl compounds? Like in here, for this 5-member ring, my plane of symmetry is in the middle. This one is here. And for right one, when we have the Fisher projection, it becomes more obvious when we do it like that. And let's do a review, and then we'll take some questions together. And so far, we went over different concepts of chirality. And let's just do a flow chart type of review and see what we have covered so far. All right. So this is a quick summary flow chart. Your textbook has a much bigger one with examples and everything. So I'll use a simpler version in our lecture. So looking at it, when you're talking about a pair of compounds, the first thing you want to ask yourself, like we know that these compounds, they have same molecular formula or not. So when we say molecular formula, we're saying like whether it's like C4H8, C4H6, like that's molecular formula. If their molecular formula are different, well, of course they're different molecules. But for molecules with the same molecular formula, you want to first ask yourself, are we looking at conformation or rotation of single bonds? So what are the examples that we did together? You can have rotation of the single bond. You can have the staggered versus eclipse conformation, so Newman projection. So you can have like staggered versus eclipsed. Right, so that's your Newman projection. Or when we're talking about the chair conformation, you can have ring flip of different chair conformation. So let's say we have maybe a methyl substituted or floral substituted chair. We can have the floral on equatorial, or you can have the floral on the axial. All right, and these are just different conformation of the same molecule. All right. And then the next question you want to ask yourself is are my molecules having same or different connectivity, given that they have the same molecular formula? So if they have different connectivity, we'll look at constitutional isomers. Like, for example, you could have a linear butane, or you can have an isobutane. Right? So the connectivity is different. These are constitutional isomers. Now, if your molecule have the same connectivity, meaning the carbon atom is attached to a carbon, oxygen, hydrogen, hydrogen, etc., you'll then ask yourself, okay, so these are molecules with same connectivity, but they might be stereoisomers. We have different types of stereoisomers. So on the left-hand side, you have stereoisomers without chiral centers. So the example here might be molecules with double bond. So for example, you can have a double bond, a difluoro double bond, versus a trans difluoro double bond. Since we're looking at a double bond, you do not have free rotation over a double bond. So in this case, these are stereo centers, but they are not chiral centers. All right. And then for molecules with chiral centers, well, you have molecules with one chiral center or multiple chiral center. So for molecules with one chiral center, so that's the example we did this morning, well, earlier today. With only one chiral center, you can have a pair of enantiomers. So this is a pair of enantiomers we did earlier today. All right, and know how to assign your RS stereo configuration for these enantiomer pairs. And if I just draw it out here, we have, well, this way, comes down, my fluorine comes out, and on the right we have, comes out, my fluorine comes out. And know how to assign the RS stereo configuration. You have 1, 2, 3. This goes counterclockwise. That's my S. 1, 2, 3. This goes clockwise. That's my R. Right. And then for molecules with more than one stereo center, we then should consider, okay, first of all, the molecule has two or more stereo center. If it's odd number stereo center, typically it's okay. But when you have like even number of stereo center, you want to ask yourself whether or not we're looking at a meso compound or a real chiral molecule. So this is the example of the meso compound we went over. Like drawing that like that is not very obvious, right? So if we draw it in this way, what we end up getting is, well, 1, 2, 3, OH dashed in, OH wedged out. We have two chiral center in this molecule, but if we change its conformation into drawing it like this, that equals to my CH3, and then all my OH dashed in. My hydrogen wedged out. And we have an internal mirror plane, and thus my molecule is a meso compound. Again, meso is it's a molecule that with multiple chiral center, but you have an internal mirror plane, making it an achiral molecule. Yes?
Wait, is the top one a meso compound?
Which one?
That.
Yeah. These are the same molecules. This is the example we did, right? So, okay, this one is that, right? So you have carbon, 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 carbon. The left one dash in, right one wedge out. They're exactly the same compound. Now I'm just changing my perspective by rotating a single bond so that I look like that. So the mirror plane becomes more obvious. And know the relationship between enantiomers and diastereomers. So if we now have a different molecule, Okay. So for this one, the one on the top. Now we're looking. Okay, the one on the top. The one we're looking at is this one, the OH-in, OH-in. All right. If we look at these two molecules, what's the relationship between this one and this one? They're diastereomers. And now this molecule is a chiral molecule, because no matter how you rotate it, like if I rotate it to this way, which is the same kind of rotation we did, you do not have that internal mirror plane. So you can rotate it any way you like. It doesn't have that internal mirror plane. And thus this one is a chiral molecule. And we can draw its enantiomer. So if I put it like that, okay. I'm just trying to organize it so it's obviously a pair of enantiomer. Let's see. This is my miso wall. Yeah, this is my miso wall. That's why I can't make it happen. Let's see. Okay, now these pairs are my enantiomer, and we can draw it. It's coming out. Oh, wait, these are the same molecule. So we want to switch both of them. That's why it's a little bit difficult when you have like multiple model kits and you're trying to build the right one. Okay, I think I messed it up again. This way, yeah. I was Alright. Now it's more obvious. It's like a mirror plane on top of each other. It's like the mirror plane is right here. And if we can draw it on paper. And you can draw it differently. I mean, this one is the same if you draw it as, which is like if I flip it this way, and I got it to both of my oxygen wedge out, that's the same kind of picture. Okay, so that's a general summary. Any questions before we move on? So now I'm gonna use the cyclohexene to do one more example with you. So, thinking about the cyclohexene, we can draw this one on the board. What is this one? This is a chair conformation. We have two fluorine on my chair that are cis to each other. So if we draw the board, draw it on the board, we have two fluorine. One is equatorial, the other is axial. So the question comes, is this molecule a chiral molecule? We have two stereocenters. Is it a chiral molecule? Now, whenever you face this question, you want to think about it. Now, this is a chair conformation. Do we have other conformation that we can easily find an internal mirror plane? So this goes back to twisting your molecular kit into, let's say, a boat conformation. All right. And now it becomes super obvious. I didn't break any bonds. I'm just twisting my chair into a boat conformation. We can clearly see there is an internal mirror plane. So this molecule is a chiral. Or this one is the 1,2 cis difluoro cyclohexene. All right. What if we have the 1,2 trans difluorocyclohexene? Now, first question, can you draw the lowest energy conformation, chair conformation of the 1,2 trans cyclohexene? I mean, 1,2 trans difluorocyclohexene. So when we look at the 1,2 trans difluorocyclohexene, so the lowest energy one will be out. You have a fluorine, you have a fluorine. So this is the 1,2 trans difluoro cyclohexane. Right. And as far as nomenclature goes, you need to know like these two are the same thing. That's the name of that molecule. And now we're looking at the trans configuration. And same thing. We can put it into the higher energy boat configuration and see whether or not we can identify an internal symmetry plane. 1 minute after I finish this. So if we put it into the boat configuration, we can see that there's no internal plane of symmetry. So my 1,2 trans difluoro is chiral. Yes, question?
Do you include the cis and trans part of the nomenclature when you're talking about?
We only include the cis and trans part of the nomenclature when you have a well-defined plane, like a plane of a ring or like a double bond. So cis means they're on the same side, trans means they're on different sides. Yes.
How are there only two chiral groups in that?
Which one?
In like either one of the, you said there's only two chiral groups, how many is it?
Well, for chiral centers, remember you're talking about carbon center with four different things attached to it.
Oh, they each have.
Yeah. It's chiral center, right? You have a tetrahedral center with 4 different substitutions attached to it. So before we conclude for today, maybe you can go back and think about it. What if you have 1,3 disubstituted cyclohexane or 1,4 disubstituted cyclohexane, cis and trans? Are they chiral, achiral, or are they meso? And I'll pick back there.